All right, welcome to my last part of what I cover in Unit 9, which is my version of mechanical waves and sound. Broke this up into three videos: an introduction video, a standing wave, and then this one is on beats and the Doppler effect. Now, a beat is something that occurs when we have two sound waves that are basically being superpositioned. And if these two sound waves are not the same frequency, the superposition sound wave, and that's going to be the sound wave that we hear, has a high-low sound to it. And so the beat is this repeating high-low sound, and it's a result of two sound waves of not the same frequency, and they are being superpositioned. Now, the beat that you hear, or the rate that the sound goes up and down, is the difference between the two frequencies. So the beat frequency is simply, I'm going to write it as frequency 1 minus frequency 2. It's one frequency minus the other. So if you have two sound waves, one is 10 hertz and one is 9 hertz, that's a beat frequency of 1 hertz. And you have a beat frequency if the sound waves are 1,000 hertz and 1,001 hertz. And it's going to be the same beat frequency. It doesn't matter whether one's high or one's low. It's just, I guess you can say, it's the absolute value. So I'm going to do two things here. I'm going to go and I'm going to attempt to go to a website and illustrate what a beat sounds like, and then we're going to take a look at a spreadsheet that I found, and it graphs a couple of waves, and it helps you see what a beat looks like.
I want to show you, both visually and through sound, what a beat frequency is. This is a spreadsheet that I found and it was apparently developed by Captain Colwell. And it's really nice because it shows a 1 second interval. I have a 400 and a 401 hertz wave, and when you superposition them, is the blue wave where you see it's really loud, really soft, really loud. And so this is a 1 hertz beat, and this is what it sounds like for 400 and 401 hertz waves. You can hear it going up and down, and that rate that's going up and down is once every second. That's a 1 hertz beat. Here's a 3 hertz beat. That's what it looks like, and this is what it sounds like. Now, finally, a 10 hertz beat using 400 and 410 hertz. This is the type of graph probably that the student will most likely be given, where they're given this type of spectrograph and they have to interpret these high-low marks are the beat, and if it occurs 3 times in a second, then that's a 3 hertz beat. If we know one of the waves is 400 hertz, you should be able to determine that the other wave is either 403, as this is, or 397, which gives us the same beat frequency. Not a whole lot of difference between the two, but they should be able to figure it out given the information in the problem.
The thing to keep in mind about the beat frequency is, if you're given one of the sound frequencies, like 440 hertz, and you hear a beat frequency of 1, the other sound frequency is either 439 hertz or 441. We don't know without more information. That's what a lot of the questions tend to get into. So you just need to be a little bit careful about that. Okay, so let's talk for a second about the Doppler effect. A lot of kids have heard the word Doppler mostly from weather and Doppler radar and things like that. I'm going to show a small clip from The Big Bang Theory where they talk about the Doppler effect. This is a clip that I show in class.
Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
This animation of the Doppler effect was created by Dr. Dan Russell, and it's really nice. I like it a lot. Here's an example of a sound source that's just sitting there. The sound waves radiate out from it in equal directions, at equal rates, no matter where you are around the source. If you're just standing there, you're going to hear the same noise. You're going to hear the same noise sound here as you would over here. If you look at the lines, the wavelengths look like they're the same length, and so you're going to hear the same sound. If the source is moving, though, as soon as it emits a sound wave, the source kind of catches up to it a little bit. And so if you're standing over here where the source is moving towards you, the waves are bunched up. It's like it has a smaller wavelength. And if it has a smaller wavelength, then the frequency is going to appear higher. And this is our apparent change in frequency. Over here, as it's moving away from us, we're going to have an apparent lower frequency, and the pitch is going to be lower. And that's what Sheldon was showing with his sound. Over here, it's a higher pitched sound. Over on this side, as it's moving away from us, it's lower pitched.
So I think the important thing, and this is what I stress in class, it's due to the apparent change. The sound frequency itself does not actually change. It just appears to change because we hear it differently because there is relative motion. Now, here's what you have to be careful about. The relative motion is between the source, the thing making the sound, and the receiver, the thing hearing it. And I'll probably spell receiver wrong. I always get that wrong. The sound source itself, and the example I tend to give is like race cars. The race car driver simply hears the same humming sound or that sound because he is moving with the sound. There's no relative motion between the source, the car, and the receiver, the driver. But if you're just sitting there, and to do my Sheldon Cooper impersonation, when you're just sitting there, the sound changes. Actually, the pitch is changing because you're not moving, but the source is. But it's relative motion. So what we could have is the source moving, the receiver at rest, the source at rest, the receiver moving, or they're both moving as long as they're not moving at the same velocity. So that's the thing to keep in mind. Both moving at different velocities. When this occurs, you will experience the Doppler effect. And I apologize for my spelling, and I'm probably running off the board. I've kind of struggled with how much of the Doppler effect the level of detail I need to go into with my classes, because quite honestly, when I look at the frameworks from the College Board, it's not particularly clear. And the people that I've asked, they've kind of gotten into it a little more, just more for information than anything else, and being able to calculate the apparent change in the frequencies and based on the two that you hear. I don't do any of that. I keep this very qualitative. I usually cover it easily within half a class period, and then I might give them a worksheet where they have to kind of analyze it, or I'll have some questions on the quiz, and this seems to be sufficient for what they need to know for Physics 1. So that kind of wraps up all my stuff with the waves. Let me just give a few highlights, since this was kind of spread out, over what I want the kids to focus in on when we're looking at waves. They need to understand the idea of superposition. They need to be able to take a couple of pulses and draw the superposition pulse. They need to be able to look at a history graph, and they need to understand when they're looking at a history graph versus a superposition graph. A history graph would be like a point on a point in a medium or on a rope where a pulse passes through it, and we want to see the displacement versus time of that pulse. So that's what I refer to as a history graph, a displacement versus time graph for a particular point in the medium. They need to understand standing waves, the harmonics, sketching them. They need to recognize, and this is one thing that I drill, that the velocity of the wave velocity depends on the medium. If the medium changes in any way, the wave velocity is going to change. If the medium doesn't change, wave velocity does not change. And so you got to look at frequency and wavelength. I was going to put down beats and Doppler, but that's mostly in the multiple choice section of the exam. These ideas right here are what the free response questions have been focusing in on. There has not been a lab experiment associated with sound waves that I recall. Doesn't mean there will be, but what it does mean is there could be. So these are the highlights with mechanical waves and sound. A fair amount of information. Kids either know it or they don't. For quite honestly, one FRQ and a few multiple choice questions on the test. But if they know it, the questions are easy. So that concludes all I have for waves, what I cover in Unit 9. I hope you found this of some help. Thanks.